Today we're going to look at section 16.1, first one from chapter 16. It's on a topic called vector fields. This is going to be quite visual, and we're going to be using some software to try and help us with that visualization. So what is a vector field? A vector field is a vector function. That's essentially what it is. The convention is, instead of calling it little f of x or capital F of x, you do call it that, but you put a little arrow hand above it like this. In textbooks, they make the f, or whatever the function's letter is, bold. So when you look at it in a textbook context, you have to look a little bit carefully. But it'll look like that, right? So that's the convention. If it's bold, it's a vector. So this function is a vector function, which means you give it a value x and y, and it becomes a vector. And this is a two-dimensional vector. This particular formula is written in terms of ij vectors, and this one is written in the way I prefer, me personally anyway, is in the component form. So this is another way of writing that. So you can erase it.
Is it the other way around? Because like the first slot is normally x, I.
Oh, yeah, but this one is that way. It could have been that.
Oh, I see what you mean now.
It just, I think I picked one straight out. Yeah, I did. This was question 1 from the homework. Now, I'll change it to that, right? So any combination of x and y here, and any combination of x and y here. So could you imagine, actually, let's not imagine that those 2's are not there now. Right. So it was back to the original. How does it work? Well, suppose I wanted to know what vector would be living at position 3, 4, right? X is 3, y is 4. Well, if you plug in x is 3 and y is 4, you get this vector. So at the point 3, 4, there is a vector. Now, if I choose another location, let's suppose I wanted to find what the value of the vector function was at, say, -3, 4. Well, that would be 4/5, -3/5. So what you've got to imagine is that you go to the point with coordinates -3, 4, which would be here, right? You go to that point. And at that point, there's a vector with these components, 4/5, -3/5, which would be along a bit and down a bit. So it'd probably be a vector, yeah, like that. Now, could you imagine this 2D space inhabited by an infinite number of points, x, y? And for every single one of those infinite number of points, wouldn't there be a vector associated with it? That entire picture is called a vector field. Now, why is that quite kind of useful? Can you imagine that you're trying to model like the surface current on a river? Can you imagine at any given point, there's eddies and curves, and sometimes it's going upstream and sometimes it's going downstream and whatever's going on. If you go to 3-dimensional, can you imagine trying to model wind? Because at any given point in time, couldn't the wind be blowing one way and then at another location blowing a totally different direction? And the length of that vector, that direction vector, wouldn't that indicate how fast the wind was blowing? So can you imagine trying to model a cyclone or a hurricane? Well, they do. They do models of all those things. Don't they have models on the East Coast? I'm trying to remember what they're called in the East Coast. Is it hurricanes in the East Coast? Right. Big winds on the East Coast, hurricanes. They can model them. And what they do is that they create a vector field model that represents what they believe the structure of that particular hurricane is, how it's moving, where is it going to hit landfall, what kind of speed is it going to hit landfall. Other examples of vector fields. Can you imagine vector field telling you a magnetic field? In fact, if the word field is at the end of whatever it is, there's a very good chance it's modeled, right? It's given a formula. That's all a model is a formula in terms of that. So vector field, there would be one. God, I'm trying to think of some now. Electric field, magnetic field, right? Things like that. All can be modeled with this guy. So one of the questions you're going to be asked right at the beginning, I think it's roughly half of the questions, is that they'll give you a vector field function like this, or maybe like that, but more likely like this, and ask you to draw it. Well, of course, you could do what I just did. And what do? They give you 4 pictures, right? So it's either picture 1, 2, 3, or 4, right? That would take you a long time if you did it by hand. So we're not going to do it that way. We're going to use software. But let me show you what it looks like in the homework so you get an idea of kind of what they ask you. Here we go. So this guy here is the number 1 that I just had. Can you see its formula written in the IJI notation? Can you see it's bold and the I is bold and the J is bold? But when we write it, we do vectors. Do any of you write funny little hats above your vector? Because that's what your physics guy people do. Do you know the one I'm talking about, the ship that looks like this?
Yeah.
That's totally fine. That's just another notation, right? I prefer the arrow, but that's me. That's what I was learning. Right, now, there are 4 pictures here. It could be picture 1, it could be picture 2, it could be picture 3, it could be picture 4 for this fella. Right. Now, I guess I could just draw on paper a couple of 100 dots, find a vector for them all, and 2 days later, I'd be able to look at that picture and say, yeah, it looks like number 3, or it looks like number 2. Right. So, not really practical, agreed, to do it by hand. So we'll do it with software. So I'm going to show you, if I can make this work, how that's going to kind of happen. Right. You should be looking at 264 Canvas page. You see there a vector field 3D and a vector field 2D guy? You can see that? Right, I'll click on the 2D guy. Oh. Are you looking at a picture of a vector field in blue? So I should be able to just click on this guy, rub him out, and put in the first guy, right? The guy that's going to go here. And that was y over square root bracket x squared plus y squared. Close the bracket. Close, right, click out of there. Yay.
We got a 2.
Yeah, I'm trying to do this leaning over, which isn't great. Yay, looks good. Now, the other guy looks almost the same, so with a bit of luck, I should be able to just click on this and copy it, Control C, and then go down here, rub out. Can I rub that out? And then go to the beginning. Okay. Evidently, copy and paste is not its friend. It might have been. No, it's not. Okay. X divided by square root. I'm pretty sure copy and paste should work, but well, if it doesn't work, it doesn't work. We're comfortable about Bob. Right.
You forgot that squared again.
Darn it in space. Where my brain is today. Yay. Okay, this might not look very vector-like, but that's because you have to move some things around. So I'm going to take this fella and I'm going to do this fella. There. Now, do you see I've now got a pretty decent looking vector field? Now, if you don't like one of the things, you can adjust it. You see if I do that, I make the little heads a little bit smaller. you know, the bit that looks like this. If I think the lines are getting in the way of each other, because if you do them too big, it's hard to see, and if you do them too small, you can't see anything, right? So there's some kind of sweet point around about there. Now, that guy is in your brain, and then what you do, you go and look at the picture, A, B, C, or D, and you pick the right picture. You see how it's going to work? Because one of them will look more like that than the other three. Now, if I was just imagining what this could be modeling, let's think of a water current issue, right? The way I tend to think of water current is, can you imagine where this mouse pointer is right now? If a boat was there, wouldn't the water current make it go away like that? If the boat was here, wouldn't the water current make it go like that? If the boat was here, wouldn't the water current make it go to here? And then we'd have an issue. And then if it was here, it would go there. And if it was here, it would come out and go out. So I have no idea what that would look like as a river, but there is definitely a weird hole in the riverbed where something really strange is happening. Either you get sucked into the hole or you get chucked out of the hole. So maybe it's not a water current. Maybe this is a gravitational field where certain things push you away and other things attract you. Right? Or it's a magnetic field, right? Just stick the word field at the end and you're probably looking at one of these. Right? So far, so good. So if you tell me a function, can we go here and do a 2D guy and pick the picture, right? So let me return back to the homework. I can't remember which one we were looking at. I think it was this one. That's the closest to it. Weren't some of them coming in and some of them coming out, but you know, whatever it is. Oh, lower down.
I think it's the bottom right, actually, because I have that
one.
curvature.
Oh, okay, right. Yeah, it's coming in and it's going out. That's exactly what it is. It's the fourth one, right? If I do have both screens in front of me. The other one's in front of me here. I should have just looked. Right. Now, can you see this vector field? Won't the first guy be X, the second guy be negative Y? And it'd be one of these pictures. Well, let's try and do it without the software. There are 4 possible vector fields, right? Great, 4 possible ones. I'm going to have to shrink the size down a little bit. Right. Which one do you think it is? Top left, top right, bottom left, bottom right. There's our choices. X, comma, take away Y.
Bottom left.
Okay, bottom left. So you're going for this one?
Yeah.
Okay, so let me do a test point and see how it works. Suppose I take a point. Yeah, there's a little bit awkward. Do you notice that some of these vectors are quite long and some of them are so small you can't see them? The length of the vector is the magnitude of that vector. So big vectors have long lines. So I'm going to choose a point that is 5,
No.
5.
No.
Change your mind? Right, 5, 5, right? That would be here, roughly. And it should be 5 along and 5 down. Well, that doesn't look like it's 5 along, 5 down. That doesn't look like it's 5 along, 5 down. That could be 5 along, 5 down. And that doesn't look like it. So I like your answer. I would have chosen the third one. Or you can go and do the 2D graph thing and see the picture. Very good. Right. The software does something. Question. The software doesn't do quite as good as the pictures. The software typically makes all the vectors the same length, even though they really aren't. This actually makes the vectors different sizes depending on how big they are. So that's more realistic. There's another one, same idea. Ah, whoa, look at that. That is a three-dimensional vector field. Can you see that the X, Y, and the Z is a fixed number? One of these four pictures represents that. Now, if you've got a great visual brain, you might be able to guess that, but I am not going to even attempt to guess that. If you hold on for a few moments, I'm going to just use some software and see what a vector field, oops, wrong one. Yeah, you have to hit a lot of buttons, unfortunately, when I do this software. Here we are.
It can't be the bottom right, because if you punch in all negatives, then you've got a problem.
Okay, because the vectors are pointing uphill. So you're saying that one is not a candidate. Yeah, I would probably agree. Not probably, I do agree. So I am now going to go out and in, and we'll show you what this one is like. Oh, darn it. Oh, here we go. Right, so this is also in your canvas. P, Q, and R just represents the guy that goes here, the guy that goes here, and the guy that goes here. And excuse me.
Oh, I'm sorry. I'm sorry.
I have fixed that problem, so we are good. Now, back to where we were. Right. Okay, so are you looking at Vector 3D software, or shall I go out and in again?
Oh, I can see it.
You can see it? This guy here, with a mouse around it? Okay, so we got a P, Q, and R. In this question, it's X, Y, and 3. So I'm assuming I should just put X here, Y here, and 3 here. And scroll up a little bit. Interesting. Orientate it a little bit. Now, from what I can see, it's definitely not 2, top right. Bottom left doesn't look too promising. Actually, it does look like it should be the bottom right. Double check that. None of these guys are pointing downwards. Can I change that in any way? No, they all seem to be pointing upwards. Interesting.
They'll never point downwards because the Z is always 3.
True. True. That makes sense. And positive up. Yep. That guy is the third picture. So that would be picture bottom left-hand side. Okay. Do you get the gist that you just use software to do pictures? First half of your section is pick the right guy for that. If you want to have fun guesstimating who it is by just picking a point like 5, 5, 5 or 1, 2, 3 or something, figuring out what that value is, and then looking at which picture does the vector seem to be pointing in a consistent way to what the answer is. And that takes care of the first part of 16.1. So let's look at the second part of 16.1. Which is called the gradient vector function. Now, this fella is not a vector. He is the normal f x, y, z equals x squared plus xy, right? Just a normal 3D vector. How do you know it's not a vector function? How do you know this is just a normal x squared plus 2xy kind of thing?
It's
If it was,
point.
what were you going to say, Ben?
It's a point in space instead of an angle and a magnitude.
Or what I was badly phrased, my question is, shouldn't there be a little arrow above the f if it was a vector function? Right. Or in textbooks, wouldn't that f be a bold f? Right. So it's just a normal function. So what's this new guy, the gradient vector function? Now, do you see it does have an arrow? You can either put it above the triangle, or you can put it above the f, or you can put it above the triangle f. As long as there's that arrow up there, everybody's happy, right? Typically, you put it above the triangle, and that way you can leave the f alone, right? So if I was trying to do it in a textbook context, technically speaking, the delta should be a little bit thicker, right? But since delta is only used in the context of this question, we all know it's a vector function because it says delta, right? So delta is only used in that. Now, what is it? It's a vector function. Do you see it? For any given point x, y, z, you get a vector. The partial derivative of x, the partial derivative y, and the partial derivative z. So you have a whole bunch of questions that say, here is this guy, find delta f. Now, we normally call that guy, for short, the grad of f. Right. Occasionally, I might say delta f, but I'll try if I can to remember to call it the grad of f. It's not just me abbreviating the word gradient. Everybody calls it the grad. If you look up a search online, you could probably just say the grad of f or the grad of a function, and you'd get good hits on that topic. Well, if you're a physics guy, you might be interested in what that vector is. If you're a mathematician, aren't you just more interested in how to get the answer? And there is one keyword that is going to be your friend in hopefully a lot of questions, but at least a few. And the word is symmetry. If the function has got some kind of symmetry to it, can't that make your workload a lot less? Because don't you probably only need to find one and you can make a reasonable judgment call on the other two? So I'm going to make my first question a symmetric function. There it is. X cubed plus y cubed plus z cubed. Agreed? Nice and symmetric. The grad of f. Partial derivative with respect to x. Partial derivative with y. Partial derivative with z. I don't really think I needed symmetry because it was too easy, but technically I could have. Let's move up the food chain. Now this time, it's not trivial, right? Would you agree it's symmetric? So all I really need to do is find one of these three, and I should be able to figure out how the others are. And I am a creature of habit, so I always find df by dx when it's symmetric. Right, you know, technically it doesn't matter, but I just do it. So let's find this partial derivative. Oh, I need to know how to differentiate this. Do you recognize that this is a really, really ugly question to differentiate? Agreed? And if I am going to differentiate it, I probably should write it in a slightly different form. Are you comfortable that you need a half power if you're going to differentiate? And no, that is not equal to x plus y plus z, and the whole answer is 1. God, I wish that was true. That would make a whole load of questions that we've done 10 times easier, but it's not true, right? It doesn't simplify that way. Now, what method from Calc 1 do you use to differentiate a fraction like this?
Quotient rule.
And depends who you got, but quotient rule is f dash g, take away f of g dashed over g squared. And the top guy is called f, and the bottom guy is called g. Happy with my naming system? And these are just placeholders, right? This f means this right now. Okay. With respect to x, and with only x in your brain, what's the derivative of x plus y plus z with respect to x?
1.
G, you leave alone. Take away f, you leave alone. Now it gets messy. I'm now going to differentiate the bottom, the g, with respect to x. So it's this mess to a half. Isn't that going to be a chain rule? And it's going to be a half, reduce the power by 1. That's negative a half. And what do I finish with? Well, shouldn't I finish with the derivative of what's inside the brackets? And in this case, 2x all over g squared. Now, if you take this guy who's to the power of a half, if you square him, don't you just get x squared plus y squared plus z squared to the power of 1? So far, so good. Any questions about the process?
Professor, in the second part of the top, wouldn't that be x plus y plus z instead of just x?
This here?
A little bit.
Oh,
Yeah.
here?
Yeah.
Okay. It should be the top unchanged, so it should have been that. You're right. So one of these gets me x squared plus y squared plus z squared to power a half. Take away, well, that times that with an x, so what do I get? I get an x, I get x plus y plus z, and I get an x squared plus y squared plus z squared to the negative a half. God, I should have started much further to the left than I did. That is one messy looking fella, right? Seem to be missing touch. There we go. Are we good? Now, style points. Oh, are you happy about the 2 and the thing and getting an X there? Right, style points. That's not the best answer. I got to make it pretty. I am going to pull out a fractional power of this guy. I have this guy to the power of a half. I have this same guy to the power of negative a half. What do you pull out as the common factor? What power? A half? Negative half. Which one? If it was x cubed in x, wouldn't you pull out x? Don't you always pull out the smaller choice? So I'm going to pull out negative a half power. That gets used up, and so I'm just left with that guy. And what does this fella do if you remove it from here? Well, it's a bit weird, but you have a half take away negative a half, which really just means, take away a half, subtract negative a half, you get 1. And 1 power just means that power. Now this thing is growing like a monster, but it is going to become something nice at the end. Can this negative a half power come downstairs and join this guy? And so you'll have 1.5 powers.
Isn't 1/2 minus 1/2 0?
1/2 minus negative 1/2 is
Oh,
1.
okay.
But what you said was true. But 1/2 subtract negative half. So it's this power, subtract that. If it was a common factor of x, wouldn't you say x squared take away 1? Right? If you were pulling out a common factor from x squared. This fella here is x squared plus y squared plus z squared. Take away x squared, take away xy, take away xz. And we are finished. We have a y squared plus a z squared. Take away an xy, take away an xz. All over x squared plus y squared plus z squared to 3/2. Whew. And that is only one of the 3 pieces. You still with me? Right, let's do symmetry. If that guy is one of the pieces, shouldn't I be able to make an intelligent assumption on, this is it, on the other 2? Right, that's what it looks like with x's. What do you think it would look like if I did it with y? Right, so do it in bits. Well, let's do the easy bit. Wouldn't the bottom be the same in both cases, right? According to the symmetry of the thing. Now let's go back to the top. When you do it with y, right, this is what it looks like with x. When it was x, do you notice that the x squared was missing and it was the other 2? So if it would be y, wouldn't the y squared be missing and it would be the other 2? So that tells me x squared plus z squared. When it was x, isn't it negative xy, negative xz? So x with the other 2. So negative yx, negative yz. I do the z one. What will the first 2 terms, if you differentiate with respect to z, get you?
X squared plus y squared.
Take away what now? The other 2 terms.
Zx minus z squared.
Z times the other 2. Right, zx, zy. And if you put those 3 together, you have finally got probably the ugliest delta f, right, grad of f, that you're likely to see. But at least we got the ugliest one out of the way. So a lot of the ones you're going to see are going to look like baby questions now, because there ain't anything near as bad as that one. Right? Are we still good? Right. So let me pick some homework questions, or ones at least like homework questions that we would, you'd be expected to do. This one is similar to question 7. The function that we're going to get the grad of. Is that guy? So it's going to be the partial with x, the partial with y, partial with z. Are you okay with me just mixing and notation just so we get used to different phraseologies? Isn't that just the same a different notation for the same event, right? Okay. I guess, would symmetry be our friend? So if I can just find one of these, can't I put the answer and then duplicate them for the other two? So let me move this guy over to the side and just focus on getting the partial derivative with respect to x. Now it's a lot nicer than the other one we did. We agree this one's not anywhere near as bad, but the partial derivative with respect to x, 2 times. Chain rule, 1/2 x squared plus y squared plus z squared. Reduce the power by 1 to get -1/2. And then times, well, what do we times with? What's left?
2x.
And that 2 and that half cancel, and that leaves me an x and a 2, so I have a 2x. And can this come downstairs as a positive? And this becomes a square root. Are you happy with the style points? Style points are factor the heck out of it and make it look like the original. Didn't the original have a square root in it, not a half power? Which is why I done all this. Right, so over here, the answer is going to be 2x over the square root of all that stuff. Wouldn't the second one be 2y, the square root of all that stuff? And then 2z, the square root of that stuff. And that would be the final answer. Are we okay with that one? Right. Nothing too weird. Are we comfortable with the symmetry allowing these two? In this particular case, an x gives you an x, a y would give you a y, and a z would give you a z. Sometimes the way you do symmetry is by what it doesn't have tells you what to use. You know, it doesn't have an x in it, so that's for the x's. It doesn't have a y in it, that was for the y's, which kind of happened the last one. Okay, let's have a look at, I don't know. Oh, let's do a 2D one, they're even easier. There's a 2D vector field, right? Nothing particularly strange about it. Agreed? Not symmetric, which means I do each one on its own, but nothing too scary either. Chain rule's very common. If you differentiate this with respect to x, you will get the cosine of x squared take away y times a 2x. Comfortable with that? Now, if you do this one, you get the cosine of x squared minus y times the derivative with respect to y, which is -1. Much nicer than the ugly one I started with. Have you noticed that these ones are nowhere near as bad? Right. This is, perfect timing. This is question 12, or like question 12. It's back to being a 3D one. And the function is x, the cosine of 2y over z. So we're going to get the gradient of f. Okay. If you want to do the partial derivative with respect to x, what would it be in this question? Partial derivative with respect to x.
Cosine of 2y over z, right?
Agreed. Partial derivative of the same guy, but now with respect to y.
2x negative sine 2y over z.
2x over z, right?
You see where the z came
I
from?
forgot the z.
Is there something else? That's it, right? Easy done. Not that I've ever made a mistake, right, guys? Okay. This one's going to be the one that's going to, you know, be extra careful, right? This last one. Any volunteers?
It's going to be negative. Okay, with respect to z, yeah, negative 2xy natural log of z times the sine of 2y
Nope.
over z.
Nope. The natural log threw me. You're integrating.
Oh, whoops, right.
But thank you for chucking in there. Another attempt.
It's going to be xy over z squared times the cosine of 2y over z.
Sine.
No.
Yes.
Yeah, I meant sine.
And there's
sorry.
a 2.
And
a 1/2. I think they cancel out.
no,
The negative.
you're integrating.
No, the negatives cancel too.
There's no,
What?
yeah, the negatives cancel.
Oh, then it's, I'm wrong. You're right. Right. So I'll take it slowly then, because there's an awful lot going on in this fella, right? So we're differentiating, not integrating, which was easy mistake. This function with respect to z. So if I write it like that, it might help. So it's going to be x, the derivative of this, which is negative the sine of 2yz to the negative 1, times the derivative of this with respect to z. So you multiply by the power, and then you reduce the power by 1. The two negatives that I missed are now there. The 2, the y, and the x are there. The z squared is negative, and the sine, oops. And now I've wrote that. Remember style points. Make it look like the original as much as you can. Are we good? Now, let's show you just, oh, before we do that, will you say hi to get attendance? It'll give me a few seconds to get myself ready for the next bit. Okay. Imagine we've already found the gradient of f, and it ends up being this guy. And we want to imagine what that looks like in the 3D world. Now, it's not easy for me to make a good representation, so I'm apologizing before I even attempt it. Right? We can imagine that's your 3D space. There are some general patterns to this model, right? This function, right? This model. Would you agree that as x, y, and z get bigger, that the vector becomes very small. Like the point 10, 10, 10, wouldn't the vector be a tenth, a tenth, a tenth? Almost nothing, right? So what that tells me is if you imagine a sphere growing outwards, as you move out on the outside skin of that sphere, imagine you're imagining an explosion or whatever, right? Isn't the vector getting closer and closer to being a zero vector? Now, what happens in the other respect? What happens as you move inwards towards the center? In other words, when we'll keep it symmetric. When x ends up being something like 100th, right? Make it decimal, 0.001, and y is 0.001, and z equals 0.001. What does that vector look like now as you scrunch towards the center? Don't these vectors get bigger and bigger and bigger? For instance, at this point here, won't the vector be 100, 100, 100? And if it was negative numbers, it would be negative 100, negative 100, negative 100. They'd just be pointing downwards or upwards. So almost nothing at the ends are really big honking vectors towards the center. And as you get closer to the center, don't the vectors get even bigger? So when you're almost at the origin, like a millionth, right, 10 to the negative 6, won't the vectors be a million, a million, a million? What would the vector look like at the origin?
It's kind of like limits from calculus 1. It's not going to exist.
Okay, we use that term does not exist as a kind of placeholder for we don't know the answer or it doesn't exist. And don't we also sometimes use it as a placeholder for infinities? And when you know a little bit about limits, isn't the answer plus infinity or minus infinity totally acceptable? What we are modeling here would be an infinite explosion. At the origin, infinite bang. And then towards the end, less and less and less and less. In a very, very, very rudimentary way, I've just modeled the Big Bang. And depends on where you are on that sphere. If you believe in the theory that the universe in the Big Bang exploded really massively at the beginning and now it's drifting apart. There's other people who believe that we're actually accelerating, in which case that model's totally useless. But if you have a different idea of the universe. Can you see how you could model an explosion? Can you model a black hole? Right? You could do a gravitational model, right? What is the gravitational force at a particular point? Right, the length of the vector would be the gravitational force, but wouldn't the direction of the vector be telling you whether you're being sucked in or pulled in? For instance, in a black hole, wouldn't all the vectors be converging towards the origin? Because I'm assuming that's where you did the black hole. And what would happen the closer you got to the origin? Wouldn't the gravitational force be even bigger? So you could imagine modeling all sorts of cool stuff. So these vector functions aren't just like a cool algebraic thing you can do. And can you see that they can actually be used to model things that the normal f of x, y, z don't, right? Don't they just tell you a value at a given point, not a vector at a given point? It's, you know, a different kind of information. Have I sold you on them, that they're cool stuff, that you can actually model things? And the engineers amongst you might one day, or the electrical engineer people or whatever, the aeronautical people will do. Don't you model wind going over planes, wings and things? I bet you that's a vector function. I bet you it is. And so you would be modeling it using that. Okay.